Welcome to this scientific lecture about the most exciting fundamental physics experiments currently underway at CERN in 2025. Today, we'll explore cutting-edge research that's pushing the boundaries of our understanding of the universe. Before diving into the latest experiments, let me briefly explain what CERN is for those who might be new to particle physics. CERN is the European Organization for Nuclear Research, located on the border between France and Switzerland near Geneva. It's home to the Large Hadron Collider, or LHC, which is the world's most powerful particle accelerator. This enormous machine is 27 kilometers in circumference and lies 100 meters underground. Picture a massive circular tunnel where protons are accelerated to 99.9999% the speed of light. These protons travel in opposite directions and collide at specific points around the ring. The first major development in 2025 is the High-Luminosity LHC upgrade, which began operations in late 2024 and is now producing remarkable data. You might ask, what does high luminosity actually mean? Luminosity in particle physics refers to the number of collisions per second. Luminosity equals n1 times n2 times f divided by 4 pi sigma x sigma y. Here n represents the number of particles per bunch, f is the collision frequency, and sigma represents the beam size. The high-luminosity LHC increases the collision rate by a factor of 10 compared to the original LHC. This means 10 times more data for physicists to analyze. Why do we need so many more collisions? The answer lies in rare processes. Many interesting physics phenomena occur very rarely. Imagine searching for a single golden needle in a haystack of 1 trillion ordinary needles. Some processes we want to study occur only once in 10 billion collisions. The second major focus in 2025 is precision measurements of the Higgs boson. Remember, the Higgs was discovered in 2012, but we're still learning about its properties. The Higgs boson is the quantum of the Higgs field, which gives mass to fundamental particles. Without it, particles like electrons and quarks would be massless. The particle mass m equals the coupling constant gf times versus over square root of 2, where v is the vacuum expectation value of the Higgs field, approximately 246 giga-electron volts. In 2025, physicists are focusing on measuring the Higgs self-coupling. This is when a Higgs boson interacts with another Higgs boson. Two Higgs bosons can merge to produce a single Higgs. This self-interaction is predicted by the Standard Model, but has never been directly observed. You might wonder, why is this self-coupling so important? It's because it determines the shape of the Higgs potential. The Higgs potential V of phi equals negative mu squared phi squared plus lambda phi to the fourth. The lambda parameter is directly related to the self-coupling strength. The shape of this potential determines whether our universe is stable, metastable, or unstable. Current measurements suggest we might be in a metastable state, which has profound implications. The third experiment involves the MoEDAL detector, which stands for Monopole and Exotics Detector at the LHC. In 2025, it's been upgraded to search for dark matter candidates. Dark matter makes up approximately 27% of the universe's total mass energy content, yet we've never directly detected a dark matter particle. Here's the composition of our universe. Only 5% is ordinary matter that we can see and touch. Dark matter is invisible, but reveals itself through gravitational effects. The leading candidates for dark matter particles are WIMPs, which stands for weakly interacting massive particles, and axions, which are much lighter hypothetical particles. WIMP masses are expected to be in the range of 100 giga-electron volts to 1 tera-electron volts, roughly 100 to 1,000 times the mass of a proton. Axion masses are much smaller, from 10 to the negative 6 to 10 to the negative 3 electron volts, which is incredibly light. MoEDAL uses nuclear track detectors made of special plastics. When a heavy charged particle passes through, it leaves a permanent damage track that can be analyzed later. The fourth major experiment involves the LHCb detector, which specializes in studying the differences between matter and antimatter. In 2025, new measurements are revealing subtle asymmetries. According to the Big Bang Theory, the universe should have created equal amounts of matter and antimatter. but we observe a universe made almost entirely of matter. This raises a fundamental question. Where did all the antimatter go? This is one of the biggest mysteries in physics. The Big Bang created equal amounts of matter and antimatter, but today we see only matter. Something caused a tiny asymmetry that allowed matter to dominate. The key to understanding this asymmetry lies in something called CP violation. CP stands for charge parity symmetry. CP symmetry means that a process should look the same if you swap particles with antiparticles and reflect everything in a mirror. The LHCb detector studies particles containing beauty quarks, also called bottom quarks. These particles show small violations of CP symmetry. The CP asymmetry parameter A sub CP equals n of b bar minus n of b divided by n of b bar plus n of b. This measures the difference in decay rates between particles and antiparticles. Recent 2025 measurements show CP asymmetries of about 0.1% in certain decay channels. While tiny, this is exactly the kind of effect that could explain why we exist. The fifth experiment uses the ALICE detector to study the quark-gluon plasma, a state of matter that existed microseconds after the Big Bang. You might ask, what exactly is quark-gluon plasma? Normally, quarks are confined inside protons and neutrons. They can never exist freely, but at temperatures above 2 trillion Kelvin, the bonds between quarks break down. Quarks and gluons can move freely in a hot, dense soup called quark-gluon plasma. In normal matter, quarks are confined within protons and neutrons. When heated to extreme temperatures, they break free and form quark-gluon plasma. The critical temperature T sub C is approximately 2 times 10 to the 12 Kelvin, or about 150 mega-electron-volts in energy units. ALICE collides lead nuclei at nearly the speed of light. These collisions create temperatures hot enough to form quark-gluon plasma for a brief moment. The quark-gluon plasma exists for only about 10 to the negative 23 seconds before it cools and quarks recombine into normal particles. In 2025, physicists are measuring the viscosity and transport properties of this exotic state. These measurements help us understand the early universe and the strong nuclear force. The sixth major research direction involves searching for physics beyond the Standard Model. The Standard Model has been incredibly successful, but we know it's incomplete. You might wonder, if the Standard Model works so well, what's wrong with it? There are several major problems. First, the Standard Model doesn't include gravity. We have no quantum theory that unifies gravity with the other forces. Second, it doesn't explain dark matter or dark energy, which together make up 95% of the universe. Third, the Standard Model has 19 free parameters that must be input by hand. A truly fundamental theory should derive these from first principles. The Standard Model is our current best theory, but physicists are searching for new physics that could address its shortcomings. The ATLAS and CMS detectors are searching for supersymmetric particles. Supersymmetry predicts that every particle has a heavier partner. So far, no supersymmetric particles have been found. The current limit is that if they exist, their masses must be greater than 1 tera-electron-volt. Physicists are also searching for evidence of extra spatial dimensions and new fundamental forces. These could manifest as unexpected resonances in collision data. The seventh research area involves precision tests of quantum chromodynamics, or QCD, which is the theory of the strong nuclear force. Quantum chromodynamics describes how quarks interact by exchanging gluons. It's analogous to how electrons interact by exchanging photons in electromagnetism. The strong coupling constant alpha sub s at the Z boson mass equals 0.1181 plus or minus 0.0011. This has been measured to about 1% precision. One fascinating feature of QCD is asymptotic freedom. The strong force actually gets weaker at higher energies and shorter distances. This graph shows how the strong coupling constant decreases with increasing energy. At very high energies, quarks behave almost as free particles. This property is why quark-gluon plasma can form at high temperatures. The quarks become weakly bound and can move freely. The 2025 measurements are testing QCD predictions at the percent level or better. Any deviations could hint at new physics. The eighth research direction involves neutrinos. While CERN isn't primarily a neutrino facility, experiments there contribute to our understanding of these elusive particles. Neutrinos are the most abundant massive particles in the universe. About 100 trillion neutrinos pass through your body every second. Neutrinos interact only through the weak nuclear force, making them extremely difficult to detect. Most neutrinos pass through the entire Earth without interacting. Neutrinos pass through matter almost unimpeded. They can travel through the entire Earth as if it weren't there. One of the most remarkable discoveries is that neutrinos oscillate between three different flavors: electron, muon, and tau neutrinos. The probability that an electron neutrino becomes a muon neutrino equals sine squared of 2 theta 12 times sine squared of delta m squared L over 4e. Here L is distance and E is energy. The fact that neutrinos oscillate proves they must have mass. The Standard Model originally predicted massless neutrinos, so this was a major surprise. CERN experiments contribute by measuring neutrino interaction cross-sections precisely. This helps calibrate neutrino detectors around the world. The ninth research area involves the discovery and study of exotic hadrons, including pentaquarks. These are particle states that don't fit the traditional quark model. Traditionally, we thought all hadrons came in two types. Mesons are made of a quark and an antiquark. Baryons are made of three quarks. Mesons contain one quark and one antiquark. Baryons, like protons and neutrons, contain three quarks. But nature has more exotic possibilities. Pentaquarks are exotic states containing 5 quarks, typically 4 quarks and 1 antiquark, or 3 quarks and 2 antiquarks. The first convincing pentaquark was discovered at LHCb in 2015. Since then, multiple pentaquark states have been found, and in 2025 we're studying their detailed properties. Some examples include PC4312, PC4440, and PC4457. The numbers indicate their masses in mega-electron volts. Understanding the structure of these exotic hadrons tests our understanding of QCD in a new regime. Are they tightly bound 5-quark objects, or loosely bound molecules of ordinary hadrons? The 10th and final topic is the planning for CERN's next major facility, the Future Circular Collider, or FCC. The proposed Future Circular Collider would have a circumference of 100 kilometers, nearly 4 times larger than the current LHC. This comparison shows the size difference. The LHC is already enormous at 27 kilometers, but the FCC would be truly gigantic at 100 kilometers around. The center of mass energy would reach 100 tera-electron volts, about 7 times higher than the current LHC. The FCC plan has 2 phases. First would be an electron-positron collider for precision measurements. Later, it would be upgraded to a proton-proton collider for highest energies. With 100 tera-electron volt collisions, the FCC could potentially discover new particles with masses up to about 50 tera-electron volts. The current timeline has the design phase extending through the 2020s, with potential construction beginning in the 2030s if approved and funded. Let me summarize the 10 major experimental directions we've discussed today at CERN in 2025. The High-Luminosity LHC is providing 10 times more collision data, enabling studies of rare processes. Precision Higgs measurements, especially self-coupling, tell us about the fundamental stability of our universe. The search for dark matter continues with upgraded detectors like MoEDAL, looking for both heavy WIMPs and light axions. LHCb is measuring tiny matter-antimatter asymmetries that could explain why we exist at all. ALICE creates quark-gluon plasma, letting us study the universe as it was microseconds after the Big Bang. Searches continue for supersymmetric particles, extra dimensions, and other physics beyond the Standard Model. Quantum chromodynamics is being tested to unprecedented precision, searching for any hints of new physics. Neutrino measurements at CERN help calibrate detectors worldwide, studying these ghostly particles. The study of exotic hadrons like pentaquarks is revealing new aspects of how quarks combine together. Planning for the Future Circular Collider aims to push the energy frontier to 100 tera-electron volts. You might ask, why do we invest billions in these experiments? What's the practical value? History shows that understanding fundamental laws of nature eventually leads to transformative technologies, though often decades later. Remember, the World Wide Web itself was invented at CERN in 1989 to help physicists share data. No one predicted it would revolutionize human communication. Medical technologies like PET scans and proton therapy for cancer treatment have their roots in particle physics research. But beyond practical applications, this research represents humanity's quest to understand the fundamental nature of reality. What is the universe made of? How did it begin? Why does it have the properties it does? The Standard Model is one of humanity's greatest intellectual achievements, describing matter and forces with exquisite precision. Yet we know it's incomplete. Every answer we find raises new, deeper questions. This is the nature of science. Each discovery opens new frontiers to explore. Thank you for joining me on this journey to the cutting edge of fundamental physics. The experiments at CERN in 2025 are pushing the boundaries of human knowledge, seeking answers to questions that have puzzled us for centuries.